all we're gonna do today. I'm excited for this one. I think it will be fun. I've just developed this new lesson, so you'll be the first to get to do this. Obviously, that's exciting, but also there might be some mistakes in it that you only notice when you teach it. So if you notice anything, please let me know. And we're gonna, I know a lot of people in ARS are starting to work with machine learning models, or maybe you heard about it and want to know more about it. And, it's a topic that has a lot of hype around it. So I thought maybe let's cut through the hype a little and say what it's really all about. And then we'll do some simple machine learning models together using R. That's the plan. So as usual, you see on the stats page, if you scroll down, there's the machine learning lesson. You've got the full text version here. If you want the full text, it's all there. And I'm going to present off the slides as well today. So if I can get this thing to go away, so I can move the tabs. There we go. So I'll go ahead and start presenting. There we go. Okay. So I'll just start with a bit of a lecture, giving you some of the background. Of course, you may ask questions and interrupt and anything like that, including the people on Teams. Please just speak up because I can't see the hand raising thing. So just speak up if you're on Teams. And then that'll take a few minutes. And then after that, we'll do some of the hands-on stuff using the Posit Cloud server, or you can use your own machine just like yesterday. So yeah, I just said we're going to talk about what is exactly machine learning, more than just, it's kind of a buzzword, so more than just the hype. What really is it? Do some myth busting and that kind of thing, and then we'll walk through two different demos of two different kinds of machine learning model that you might use in your work. And so now that you've had some exposure to R and stats yesterday, you all meet the minimal prerequisites for doing this, and I think also can be beneficial if you have some experience with model syntax and tidyverse in R, which we also did yesterday, because we're going to be using some of that today. Same format. I've got a worksheet that's already loaded on the demo server, but if you're using your own, you can get it off the website, and it's got blanks we're going to fill in. And I'm going to just give you these learning objectives. We'll keep those in mind. And at the end, you can see if you learn these things. We're going to learn what is machine learning, how does it relate to statistics, what are the similarities and differences there, do some myth busting, talk about prediction versus inference, what that is. And then we'll talk about some more technical things like training models, loss functions, different types of machine learning, supervised and unsupervised, and kind of go through the steps of what you do if you want to fit a machine learning model to a data set. That's what we'll be learning about today. And the practical skills that I'm going to try to impart in the demos is how to, if you get some data for a machine learning model, how to explore that data and process it before you actually fit the model. We're going to do two kinds of model: random forest, you may have heard of. I'll explain what that is, and lasso regression. And we'll use cross-validation to fit these models. And we'll use a package called Caret in R, classification and regression training is what that stands for, and to fit the models. So let's start out by talking about what is machine learning. And these are all the kind of like, even if you're not in any type of science or research field, you can't avoid, it's in the news, like people talk about ML and AI and all this stuff. So what is it exactly that's like got everyone so excited? Well, let's talk about a few myths around machine learning, and hopefully I'll convince you that they're just myths and not really true. So yeah, statistics is like not a sexy topic these days. It's like old, boring. a statistician is like some out of touch like person who's uses old and outmoded methods, but like data scientists doing machine learning are like the cool kids. They are following the hot topic, right? And like the thing is, with statistics has been around obviously a long time. We talked about some of the history of it yesterday. People sort of like understand its limitations a little bit. Machine learning is being hyped as this hot new thing, and like people are seeing what it can do, but aren't as aware of its limitations. And basically, a machine learning model is a statistical model. Like if you're doing machine learning, you're doing statistics, and we all know statistical models are based on assumptions about the world, and a model is only good if the assumptions are true or close enough. And also, a model has to be fit to data, and if you fit it to bad data, it's not going to represent the world. So like a model's only as good as its assumptions and its data. That's going to be true if it's a simple linear regression that's just plain classical statistics, or a fancy machine learning AI model, whatever you want to call it. So I think this comic is funny. It's like, once you dress up your statistics and call it machine learning and AI, people flock to you and throw you money, So that's kind of how we statisticians see it anyway. Okay, so it's also something that maybe some people find intimidating as well. Like, okay, why do I need this? This is it's very complicated, it's different, it's new. Let me, I don't need to mess with it. Well, yes, I mean, that's not completely wrong. Like some of these models are complicated, and to truly understand exactly how they work does require a pretty high level of understanding of the theory, the mathematical statistics behind it. But if you're sort of an applied scientist and think of models, whether it's statistics, machine learning, or whatever, as a tool, you don't need to understand every aspect of how it works to be able to use it. Just like, you drive a car maybe without being able to articulate exactly how every part of it works. And there's a lot of tools out there that make it easy to do these kind of models, in a way too easy in some cases, because you can just put in data and get a result out without understanding at all how you got it. So I think somewhere in the middle is good. You don't have to become an expert at exactly all the theory behind it, but you also don't want to go into it completely blindly and just see it as just a total black box. Having some moderate level of understanding, I think, is where you want to be as an applied scientist. That's my opinion. I think that's sort of the happy medium. Okay, another hype. I mean, if there's another even more overhyped thing than machine learning, it's big data, right? It's like big data this, big data that. I mean, that's kind of, you can't escape that term either if you live in our society these days. So you might think, well, I'm, not working with big data. I just have like I'm collecting agronomy trial data from a modest number of plots. Like it's a small spreadsheet. You don't really can't fit a machine learning model because you need big data. Well, yes and no, because there are very, very large data sets. I mean, in ARS, you would think of genomic data, and anyone who's working with imagery obviously is a very big data set as well, and those really do benefit a lot from machine learning techniques. But even with small hand collected, manually collected, not automated data sets, you can still fit machine learning models and get useful insights from. So it doesn't have to be big data. And lastly, I just said, you could say, well, even you could make a good argument that you can get everything done without machine learning. You don't need to learn about it. Well, I think even if you personally do not want to fit machine learning to your data, you do need, as a scientist, to know about it, because these techniques are being applied across all scientific fields more and more. The focus in many fields is shifting from statistical inference to predictive modeling. That's like changing the entire paradigm of research in a lot of ways. So even if you don't want to do it, you should know about it and understand it a little bit to understand like where science is moving. So like being literate in some of these things is important if you're a scientist. So that's what I'm trying to do. You're not going to become an expert after 2 hours of this, but you might have a bit of literacy and understand a little more about it. That's what I'm trying to achieve. Any questions or comments so far? Yes.
Based on my limited understanding that we want to use the machine learning to deal with like it can like do more complex data or it's like longer that you think answers after or just
Yeah, I mean, so for people on teams that didn't hear that, the question was, does machine learning help with more complex data sets or help get results faster? I mean, I would say, I don't think it's faster per se. I think the some of the advantages are that it does better with complex relationships between variables. If things are all linear relationships, linear regression does just as good as a more complicated model. But if the relationships are more complex, or if you have lots of variables, then especially if you have, in the case where you have very, very large number of predictor variables and a small sample size, like say genomic data, you might have a few dozen organisms you sampled, but thousands of SNPs, which are like the variables. There, classical statistics has trouble, and machine learning is almost essential in that case. But yeah, I don't think it's faster necessarily. I mean, it's computationally a lot more intensive. It's slower, if anything, than a classical statistical model. So there's trade-offs. So now that we've got through some of the myths of what is not machine learning, well, it's a machine that's learning. That means you can define machine learning. I mean, when we say machine, we basically mean a computer. Any job that you can give a machine to do, that the more data it gets, the better it can do that job. It learns from the data. So that, and well, that sounds a lot like statistics too, right? So a statistical model can be seen as a machine learning model, because the more data you would give, say, a linear regression model, the better it can do at estimating the regression. Yeah, it's a machine. A model is a machine that takes data as input. You crank the crank and it spits out predictions as output. That's like what a statistical model is. It's also the more complicated machine learning models. So if the model is good, the more data you have, the better the model will be at its job, which is to make predictions. And what are these jobs that I'm talking about? There's sort of two main ones that we can distinguish between. One is classification, that is predicting which discrete category something belongs to, and the other is regression, when the prediction is a continuous variable. Is that coming from mine? Not sure. Anyway, yeah, classification would be like trying to predict what whether or not an individual, if you have images of a leaf, predict whether or not it has a disease on it based on that would be yes or no. So it's classification. Regression would be predicting a continuous outcome. You could predict yield or something like that, a continuous variable. Those are the two. Machine learning models usually do either classification or regression. And when it comes to classification, there's two main kinds: supervised classification and unsupervised classification. What does that mean? Supervised means we already know what the categories are that we're trying to predict. And we want to try to find patterns in the data that, if we get new data points, can help us predict what they belong to. Unsupervised would be we just get some data and we try to find clusters or groups in that data without having in advance knowledge of what the groups are. So like the left hand would be supervised because we already know like the colors representing categories. The right hand side, you know, before you draw those circles on it, that's the data, and you try to find where the clusters are. What are some examples of that? Let's say supervised would be if we're in medical research, we could have a data set of patients with different variables, clinical measurements taken on them. We know that some of those patients got heart disease and some didn't. Our goal is, if we get a new patient and take those same measurements, can we predict whether that person is likely to get heart disease or not? But we already know from our data what the two outcomes are for those patients that we have the data for. Unsupervised would be like algorithms that, like Google News, right? If you go to Google News, it sorts out the news articles by what event they are related to, right? And so when they have a very sophisticated machine learning model that takes text of the articles and tries to figure out if some articles are related to each other, if they're about the same event that happened. But it doesn't know in advance that there are specific events. It just says, well, these 4 articles have a lot of similar words and sentences in them. They're probably about the same event. But it doesn't know in advance how to categorize. So it uses an unsupervised algorithm to, when you go to, any of those news sites, use something like that. And, you could probably imagine that supervised learning is like ideal if you have data that actually says what categories things belong to. You could probably make a better model than just trying to guess. But you don't always have access to that quality of data. So if you're doing some really big scale thing like Google News is trying to do, you might have to use unsupervised learning. Any questions? Yeah, those are the two main kinds of classification tasks, supervised and unsupervised. So some of you may already be familiar with this, but what kind of machine learning are people here at ARS doing? Well, at least from the experience that I have with people in Southeast area, obviously a lot of breeders are doing genomic selection to be able to essentially predict traits of interest from genomic data. They use, in many cases, machine learning, not always, but they use a lot of machine learning models for that. I know there's a lot of efforts going on with drone imagery to take pictures, aerial photos of crops, and identify which of them contain different weed plant species. So that's a machine learning classification task. And there's also some researchers in Southeast area that do a lot with gut microbiome. They basically have mice and rats and feed them different diets and look at the species of bacteria that are living in the gut of those animals. There's hundreds and thousands of species in there. You can use machine learning models to see if there's relationship between what bacteria are in the gut and the diet or other outcomes of interest. So a lot of folks in ARS are doing machine learning models. Okay, so just to show you that it's relevant to what you all might want to do. So machine learning models are kind of all about prediction. And what is prediction and how is it different from inference? Well, so a classical statistical model is usually used for inference, meaning finding patterns in the data that tell us something about process that's going on in the world. So it's kind of like the causal modeling stuff we were talking about yesterday is all about inference. We want to know why is something happening. If your goal is prediction, this is like, it's the opposite of yesterday. Yesterday was about why, today is about how. We find patterns in the data and try to make a model that will correctly reproduce those patterns. We don't care why, what might be causing the other. We're just trying to reproduce a pattern in the data so that we can make predictions, predict the outcome on new data that we don't know the outcome for. It doesn't matter if that's not a causal relationship, as long as we get good predictions. We're just sort of in it for the practical outcome. We're not trying to understand patterns, why things are happening in the world. So yeah, you remember the shark and ice cream example from yesterday. We'll hit that again. So yes, I just said it isn't essential for predictive model to truly capture the causal relationships. As long as the correlation is there, you're going to make good predictions. But the machine learning model, any model, statistical or machine learning, that actually does encompass those true causal relationships is going to be a better model. Like, let's say, right, remember that we said shark attacks are highly correlated with ice cream sales. You could make a statistical model that would like to see how much ice cream you're likely to sell by measuring shark attacks and then using it to predict. That would actually work fine if they're highly correlated. But what, because the confounding variable is affecting both. But what if that changes? What if, shark fishing increases in that area and then the correlation breaks down? Well, then your model will fail. So it would have been better to make a model that uses the true relationship, because it's going to be more robust. It's going to have that the true relationship is embedded in the model. Like if you use temperature or whatever it was, that's a better model than using sharks to predict ice cream. Even if it would work, it's more fragile because there's not a true relationship between them. It's only confounded. Hopefully that makes sense to you all. So the more the model corresponds to what's really going on in the world, the better. Now we're going to get more technical. This has kind of been big picture so far. Now we're going to get more technical and get into the nuts and bolts of these models a little bit. So the way a machine learning model works, or any statistical model basically, is we try to find parameters that minimize the value of a loss function. What is a loss function? It's basically a function that represents the error in your predictions. You want to make that as low as possible so that your model makes the best predictions. A linear regression, classic y by x model, has a loss function, which is, if you know your stats, it's the sum of the squares of the residuals. The distance, basically, the residuals is how far are the data points from our line squared. The smaller that is, the better the line fits the data. So we try to minimize the sum of squares in a linear regression. Some machine learning models use the same idea. They try to minimize the mean squared error. That's the same as minimizing the sum of the squares of the residuals. So that's like the same as a linear regression. You don't have to use that though. Sometimes you could use mean absolute error instead of minimizing the sum of square distances. It's just minimizing the sum of the distances from the fitted line. They're slightly different because it depends on how sensitive you want that to be to the outliers, to the extreme values. That would be for regression. But if you're doing classification, you have to use a different loss function. I won't get into the details of it too much, but the basic point I'm trying to make is that anytime you have a model, machine learning or not, you have to pick some function that you're trying to optimize that tells you how good are your predictions, and you want to make that as low error as possible. And when it comes to making predictions, we want our model to strike a balance between underfitting and overfitting. To do that, we use something called regularization. So this is on the right, you could see an example of an overfit model. That model follows sort of random noise in the data too closely. So it's not going to make as good, it's fitting too close to the original data. It's not going to make good predictions on new data because it's just, the model is just reproducing random noise that happened to be in that data set that same random noise isn't going to be in new data. So that model will not make as good of predictions. But the model on the left is underfit, right? Just fitting a straight line to that is not fitting the data closely enough. You're missing a true pattern that's going on, and that pattern will be in your new data, so it's not going to make good predictions on your new data. You want like the sweet spot that is just right. It like the middle one, I would say in this case, captures the overall pattern in the data, but doesn't capture the random noise in the data. You want to be right in between. And you have to use a technique called regularization to do that. And that word is kind of like, you don't usually hear that word in a classical statistics class. It's more thought of in machine learning, but if you do any variable selection, like trying to get rid of variables in your model to get a better model, if you do model selection, if you do random effects, any of that is also considered regularization. Anything that makes a model a little bit simpler and more general, more able to capture the general patterns, not just the noise in your data set, any of that is regularization. So we're going to be doing that in machine learning. So the hard part, though, is finding that sweet spot. How do we exactly know that we're hitting that balance between overfitting and underfitting? Well, there's you can't fit your training data, the data that's used to build the model, too closely, but you can't underfit it either. What machine learning models do is you have a regularization parameter that determines the optimal level of regularization to get you right in between overfitting and underfitting to hit that middle spot. We'll talk about how we figure that out a little bit more when we talk about how to fit a machine learning model. So in machine learning world, they usually talk about training data and testing data. Training data are the data that you use to fit the model, to build the model, estimate the parameters. And then you figure out whether those are good parameters by evaluating the model on a different data set. We call that the test data set. Ideally, you would want those to be completely independent from each other, so that you're not capturing the same random noise is not shared between those two data sets. If it is, your model is going to be fit off random noise. And when you do have that issue where they're not independent and random noise between the two data sets is shared, we call that data leakage, and that's a bad thing. You want to avoid that. But the issue, the limit to how different, how independent the training and test set can be, because we want our model to be able to produce accurate predictions in a new context, away from the data that we use to build the model. That's called transferability. We want our model to be able to transfer to new situations. Like if you did a breeding trial in your field out here and said, well, this variety is very good, that's a prediction. We want that to be transferable and not just apply to that field. We want to say, well, if we release that variety and plant it somewhere else, it's still going to be best, right? That would be a successful prediction. But obviously, if you did the variety trial here in South Carolina and then, planted that variety in another field somewhere a few miles away, it's more likely to be good than if we, say, planted that variety in Florida or in, somewhere far away. The further you get from the original data, the less accurate that prediction is likely to be, right? Because you're taking it to a whole nother environment. So you have to strike a balance. The evaluation should be independent from what you use to build a model, but not too far. If you just tried to validate off of planting those varieties in Montana, it's not going to make a good prediction. So there's only so far you can extend your predictions, right? You can't extrapolate infinitely off of a model. So you got to strike a balance there. Any questions? Yes. Yes. So data leakage means the situation where we get some data that we're going to use to build our model, estimate parameters, and then we want to evaluate the model on new data. So let's say try to think of a good, and so data leakage would mean there's some random factor that's shared between the two data sets. So like, right, again, in the example, let's say we're testing a breeding trial where we're like evaluating some varieties, and then we want to say, okay, we'll plant it. Like, let's say, the let's say that like it was an extreme drought whenever we planted the varieties, and then the variety that we said was best is only best because of its extreme drought conditions. If we then evaluated that under those same conditions, it's not going to make general predictions because there's not independent. Yeah, so that would be like data leakage. So, but oftentimes the problem is when I just said we want to find a training data set and a test data set. Sometimes you don't have an independent test set that you can use. You just have your data set. That's all you have. I mean, that's pretty common, right? So what you have to do is instead of having a separate training and test data set, you have to take a portion of your training data set and set it aside to use as test data. You don't use that portion of your data set to fit the model. We only use it to test the predictions and make sure it's a good model. And so the model never sees that data when it's estimating the parameters. It's only used to evaluate. And some people are like, well, why would you do that? That's a waste of data. We want to use all the data we have to make the best model. Well, if you want your model to be general and make predictions on data that it's never seen before, you need to hold some aside and have something to evaluate it with. So I would say 10 to 20% of the data, if you're doing a machine learning model, should be set aside if you don't have a truly independent test set. And right, so this is where the data leakage can really be a problem, because you would want to, let's say you have a randomized complete block study, you would not want to set aside a few data points from each block, because then the data points you set aside are not going to be independent. You would want to like take an entire block and set it aside, because that block has its own unique environment. And so it would be more independent from the data that you are using to build the model. Did you have a question? Yes. It is the optimal ideal situation. Sorry, for people on Teams that couldn't hear that, the question was, wouldn't it be a problem to set aside some of your data set as testing because it's not independent and it would cause data leakage? Yes, it's not perfect. The best thing in an ideal world, you would have a totally independent test set to test your model on, but you don't always have that. So this is the best you can do in that circumstance, which is a common circumstance, that you have to just do all your validation internally on the data set. So the best you can do is set aside part of it, but make sure that it is as independent as possible from what, yeah, it's the best you can do. You can't eliminate the problem, but we can minimize it. Yes.
Data set that has
Yep. Yep. Yes, that would be a good example, right? Like if you had a repeated study over several years, you could build the model off of some of the years, hold 1 year aside as evaluation set, because that's going to be reasonably independent. If the environments in each year are more or less independent, then you would have, yes, that would be a good example.
Or lack of data issue with machine learning or deep learning, you suggest using multi-taro or data.
I see. Yeah. So some people, the question is, if you only have a small data set, can you like generate simulated data? Yeah. So some people do that and it can help. Right. Because again, our goal is prediction. Like if you get good predictions, who cares how you got there? If you simulated data, whatever, like we're building a tool. Like this model is a tool to make predictions. If it works, that's what we care about. So yeah, if it works, then yes, by all means, you can do that. You know, it's not going to be as good as if you had real data, but it can be okay. Because the more you simulate, the more you're getting away from the data. You're making assumptions. Those aren't real values. They're based on assumptions, and so it's less likely to make good predictions, but it still can help. Okay. Now, the next point I want to get to is thank you for all the questions, by the way. The next point is what are the practical steps we take when we get a data set and we say, well, what are we going to do with this data set? Well, just like I said yesterday, you have to start by looking at the data. You can't just throw it into a model without even looking at it. Now, in terms of pre-processing, that's when you look and see, well, some of these data points are wrong or invalid, like the sensor was broken and gave zeros. That's not possible. We'll remove that. But what about what people call outliers? That is not necessarily a good idea to remove outliers just because they're extreme high or extreme low values. If they are true data points that were generated by the, by the process that you're trying to model, well, yeah, you can remove them in your training set, but what about when you're making predictions? If you have X and Y data, you want to use X to predict Y, and you have some Y values that look weird. Yeah, you could remove them, but when you're trying to make predictions later, all you're going to have is X. You're not going to have Y, so you're not going to be able to remove outliers then. So it's if you do it, if you remove outliers just because you don't like them, that is not going to help you make predictions. You want to make your model be able to deal with those outliers instead of just getting rid of them. But if the data point is an error, yes, of course, get rid of it. But yeah, it's just something to be aware of. Another important step when you're pre-processing data is to remove features that are not going to help your prediction. Now, feature is another term you're going to see in the machine learning literature. It just means an X variable, a predictor variable. But like the cool kids at like Google and everything call them features, not X variables. So if you want to sound like a data scientist, you have to call it features. Basically, if you have a model you want to fit and you have a bunch of variables, features that you want to use to predict your outcome, some of them are not carrying any information because they don't have any variation in them. Like if every single data point has the same value for some X variable, it's not giving any information. You can just, you don't need to use it to fit the model. Or if it has very, very little variance in it, like if you have 1,000 data points and for one variable, all of them except 2 are 0, that's giving you almost no information. It's not going to help you explain any of the variation in the Y because there's no variation in X that's going to help you explain that. So you could basically, it's going to do almost nothing to help the prediction, and it's just going to make the computation slower to have that in there. So you could get rid of that. Or if two X variables are very, very highly correlated with each other, like 0.95 correlation, that means if you know that one, you know the other. The second one is giving no additional information to you that you don't already know. Putting both those variables in the model is not going to help you predict Y. It's going to just slow things down. So just keep one of the two. Again, because we don't care about causation, we're just making a predictive model. It doesn't matter which one you get rid of if they're so correlated. One is one. If you know one, you know the other. So you can just get rid of any one of them you want in a machine learning context. Another thing that you have to do when you're pre-processing your data, which we talked about yesterday a little, is that you have to standardize your variables, usually meaning transform them to be on a common scale. So what a lot of people do is Z transform, normalize all the variables so that the mean is 0 and the standard deviation is 1. That's called Z transformation. And the reason you would want to do that is because the variables might have different magnitudes, and you don't want the model to overvalue one variable just because it's, measured in micrograms and goes from 0 to 10,000 versus another variable that's measured in degrees Celsius and just goes from 20 to 30 or whatever. It's you don't want it to overvalue one and not the other. So yeah, just standardize them all so they're kind of on the same order of magnitude. And if you do that standardization, you have to do it separately on the training set and the test set. Otherwise, you've got data leakage because information about the mean of the training set will get put into the standardization of the test set if you don't do it separately. So you always have to keep those training and test set in with a wall between them, and never do some computation that affects both of them because it's going to cause data leakage. Yes, come on. For your X variables, it doesn't matter that much. It can if you, it depends, I guess, on your question. But in statistical models, there's no requirement that the X variables follow any certain distribution. It's the response variable, the Y variable, if you're doing an ANOVA type model, it has to have normal errors. There's no requirement of the distribution of X, but sometimes people do try to normalize their X variables as well, because so you could log transform them so they have better properties. It will give you a slightly different, again, if it helps your prediction, you should do it. That's kind of the fun thing about the machine learning. You can do anything you want to the data as long as you get a good result. You could try anything. It's not going to matter because what matters is does the result, is it good enough? So yeah, definitely worth trying. Now once we have got our data set where we want it, now we're going to actually fit the model. And as I said, we have the model has parameters, and it also has special parameters like the regularization parameters that help set how overfit versus underfit the model is and get you right to the sweet spot. So we want to estimate all those parameters so that we get the best possible prediction with the lowest error. We're using the test set to estimate those parameters, and we see if it's good by looking at how much error we got. We're using the training set to estimate the parameters, and then look at how much error we get on the test set. So some of the parameters are just like classic regression parameters, like intercepts and slopes. They're looking at the effect of the predictor on the outcome, and some are called tuning parameters. You might also see the term hyperparameters. Those are special ones that help set the balance of regularization, overfitting versus underfitting. We have both kinds of parameters. So how do we do that? Well, another way, instead of just splitting it up into one time in between training and test, if you just have one data set, what a lot of people do, and what we're going to do today when we actually do this in R, is called cross-validation. You may have heard of that before. It can be used in the statistics world, not just machine learning. What cross-validation is when you split a data set up into training and test set more than once, and keep doing it many times until all data points have been used at least once in the test set. So what you do, let's say you have data that you split up into into any number of groups. 5 is a common number. They're called folds. What that means is we're going to take 80% of the data, use that to train the model, and see how well it does to predict the other 20%. But then we're going to have another training set that's instead of using these 4 20% blocks, we're going to use these 4, and use this one as the test set. Then we're going to use this one as the test set, then this one, then this one. Now, since we've done it 5 times and every time we use the different 20% of the data as the test set, we have predictions for the entire data set as a test set at least one time. So every time whenever we use the model to predict number 5, the model was only trained on 1 through 4. It never saw 5. And whenever we use the model to predict 4, it was only trained on 1, 2, 3, 5. It never saw 4. So we've got like good predictions for the entire data set that the model didn't see that data point when it was trying to predict its value. So we can use this to identify the best tuning parameter that balances between overfitting and underfitting, because what we do is we use the tuning parameters, do the cross-validation, see how good a prediction it gets. Then we use a different value of the tuning parameter, do the whole cross-validation, see how good of predictions it gets. Keep doing that for many, many values of the tuning parameter until you find the best one. And then there might be more than one tuning parameter, so we'd have to do that for multiple of them. We figure out which one minimizes the loss function, which one gives us the best performance, the best predictions with the least error, and that's what we use for the final model. That's what cross-validation is. That's a bit confusing, so hopefully it will become more clear when we actually do it on a real data set. But that's a very common technique in machine learning and in statistics too. And if you do cross-validation, it's, so I say we have to split it up 5 times, do it for every tuning parameter. Then some people repeat that entire process again for a different random splitting of the data into 5 groups. Keep doing that. So you split the data up randomly into 5 groups, figure out the best tuning parameter. Then you do that again, split it into another different 5 groups with a different randomization, and do it again. You do it many times because you just in case that particular random splitting into 5 groups gave you a weird value. You do it many times to get the average over all those. And as we were just talking about with data leakage, if you have any structure in your data like blocks or anything like that, you have to, when you're doing these cross-validation folds, you have to split up and keep the blocks in separate folds. Otherwise, you'll get an overinflated estimate of how good your model is, because you're going to have, you want to keep the blocks separated when you do your cross-validation folds, if that makes sense. You don't want to have a few data points from block 1 in this fold and a few data points from block 1 in this fold. You want to have all the data points from one block in the same fold. That will, otherwise you have data leakage. And now that we have done this long process of cross-validation, we, usually what you do is you have your training set and test set, and then within the training set, you do the cross-validation. And then we have a whole nother test set that we can, now that we have our cross-validated parameters, we see how well does it do, how well does the model do predicting on data it's never seen before. And how good is good enough? That's up to you, right? There's no significance threshold, 0.05 or whatever. It's just, is that performance as good as you need it to be? Like if you are trying to predict yield, does it predict it within, 10 kilograms per hectare? Maybe that's good prediction, maybe it's bad. Maybe you only need it within 100 kilograms per hectare, or, it just depends on the applied goal. There's no statistical significance. It's just how good, or like, did you predict heart disease 90% of the time correctly? Maybe that's good. Maybe it's terrible. Maybe you need it to be 99.9%. I don't know. I can't answer that question for you. What matters is your needs, your like science goals or applied goals is how you determine whether the model is good enough. There's no good or bad. There's just, does it meet your needs? And just to reiterate that with a graphically, what we usually do when we have, this is the full-on workflow for tuning and validating a model. First, we get our data set, we split it into training and testing. Or we might have an independent test set, which would be even better. But if you don't, you have to just split it within the data you have. Then inside of that training set, we use cross-validation, figure out the parameters. Then we take our model and use it to predict off the testing data and see how well we did. It might be good enough and it might not. It just depends. That's kind of the steps we'll take. And there is, I just was talking about prediction. All we care about is prediction. You can also use machine learning models to make statistical inference about what parameters are important for predicting, or what variables are important for predicting your outcome. There's a lot of different methods out there to quantify that. I'm not really going to go into that today, but I just wanted to mention it, that you can, there are ways to use it for other things besides just prediction. You can actually like look at which variables are most important for prediction. And you could use that to like say, well, maybe those are causally important. And another fun thing about machine learning, again, is that like if all we care about is prediction, you can, there's sort of no holds barred. You can do whatever you want. There's many different kinds of machine learning models, many algorithms out there. You could just like try out a whole bunch of them and use the one that gets the best results. There's no reason why not, right? I mean, as long as you use regularization and make sure those models are not overfit, the one that has the best results on independent data is the one you should use. So you could just like try out many. Now, some of them are very, when you get into like deep learning, neural networks, all that kind of stuff, they get to be very complicated to explain exactly what it is they're doing. Even if they get better predictions, maybe more complicated is not always better. It could be too complicated to actually understand what it's doing. So I feel like you want to have one that gives good enough results, but also that you can at least somewhat understand what it's doing. I think that's like, that's kind of the best ideal. Now, you might say, hey, that cross-validation and testing on an independent data set would work for just a classical statistical model. Any regression, you could do that. Why don't people do that when they're just doing a regression or an ANOVA or whatever? Well, I don't know. They should honestly do that more because it protects against overfitting. We don't really want to overfit if we're just trying to learn about something and not necessarily make prediction. If we want to understand the world, we don't want to overfit either, right? It's still a problem. And I think part of the reason that like we have a reproducibility crisis in science and a lot of junk science is out there that's getting published every day is because people are like mining data to draw conclusions when they're really just fitting to random noise in their data set. And yeah, I think there's, I mean, if you go and like survey the recent literature, you'll find papers like that being published every day. And I think one thing that would help with that is if we did in classical statistics adopt more of these techniques with cross-validation and externally validating a statistical model on a new data set. That would help a lot. It would help if we're trying to predict, and it would help if we're trying to make inference to learn about the world. Why shouldn't we all do that? Yes.
And now you may have said this, I apologize, but what you're talking about is controlling type 2 error, right?
So like, yeah, I mean, both. It would do both, right? Underfitting would be like a type 2 error because we are failing to detect the true pattern that's there. Overfitting is a type 1 error. It's a false positive because you're saying a pattern is there that's only random noise. So it's both.
Okay.
Yep.
And what you're saying, I think, is cross validation and external validation.
Yes.
Are the only technique to hold for type 1.
Not the only, but they are very good techniques to help with that. Yes, because they are yeah, I mean, whenever you do a mixed model with random effects, that can help control the type 2 error. Whenever you do model selection, variable selection, that's also helping with type 2 error because it's getting rid of variables that aren't explaining. So yeah, they're all part of it. And yes, it's yeah, you're definitely right though. And we're almost done with sort of the background. A couple more slides. I just want to say that we're going to use R today. When people think about machine learning, you probably might think that like people tend to think Python is like the language that everybody uses in machine learning. And it's like, well, why aren't we using Python? Because it's the best one. But I don't think that's necessarily true. I think that you can do good machine learning with any software. Yes, even SAS has machine learning libraries and they work pretty well too. So, but I just know R best, so that's what we're going to use today. But I think any of them are good. And yeah, I just want to also make a cautionary note before we go into actually. We'll take a break after this and before we do the hands-on stuff. But I would caution you against using, you know, too much black box where you just like take some software that's like, here, put in your data and get a prediction without understanding what it's doing. Yes, I think it's good to democratize and make things more accessible. Not everybody knows how to code that well, so like I think it's fine. But the flip side is it can be dangerous to have results that you don't understand. It shouldn't just be a pipeline that any data you get, you throw in and get a result. It's always better for each new data set you get to look at it and customize or use the model that's most appropriate to that situation. And there's an R package called tidy models that you might see if you start doing machine learning in R. I feel like it kind of goes too far where it like kind of does a lot of stuff for you automatically without you being able to like make the decisions that you need to make sure it's appropriate. So a lot of people use that for intro tutorials, but I didn't want to because I think it takes too much out of your hands and does too much automatically. Once you get a little better at it and understand it a bit more, you could maybe move to that because it makes things more efficient, but I'm not going to use it today. And this, getting to Todd's point, I think let's go to the big picture. What we want to do as scientists or as people trying to make predictions is make predictions that are true in the real world and aren't just specific to our data set. Machine learning models do that because they use the regularization parameters so we don't overfit and make good predictions. If you do any mixed models or variable selection, there's like the random effects help you not overfit your data and make good predictions. If you do Bayesian statistics, you use prior distributions that help you not overfit to your data and make good predictions. So no matter what, you're trying to not overfit or underfit your data and make good predictions. They're all kind of trying to do the same thing, and they're all tools for the job. The more tools you as scientists know how to use, the better. So I would say it's good to know a little bit about all this stuff, and there's overlap between all these things as well. So that is the end of the background part of this. Let's take a 10-minute break, and when we come back, we will talk about this first demo. So let's see, what time is it? It's 10:02. So at 10:12, we'll come back and do the first walkthrough. So yeah, we had some good questions in the break, and we Are there any other questions anyone has about the stuff we talked about already before I get into the actual demo part? Yes, Eric.
Yeah. This is kind of an abstract question, but
Sure.
Is there any, I doubt you can give like a threshold for what level of data, like the number of data points you would need to necessitate actually using machine learning
Yes. How much?
models?
Yeah. I mean, so yeah, the question was how much data is needed to fit a machine learning model? I mean, it depends on the goal of the research, you know, like, I mean, a lot of clinical research and like biomedical stuff, even if it's on mice. I mean, they have only, it's not like they have thousands of mice. They might just have like a few dozen mice where they did sequencing on it and have a lot of SNPs that they're looking at. So like you could do a machine learning model on that. There's with a small, it's sort of, it's not necessarily how big the data is. It's like what the shape of the data is. You can have either like wide data means you have a lot more variables than you have data points. Long data would be having more data points than variables. If you have really wide data, that's good for machine learning model. And yeah, so, you know, yeah.
You've got some plots out here I told you about yesterday.
Yeah.
We have remote sensing
Okay.
equipment in, but it's only in like one replicate.
Okay,
so it's
sure.
like what you were saying, very narrow data,
Right.
but it's a very dense set of narrow data.
Yeah. Yeah, I mean, that would be a good candidate to use machine learning to like get rid of some of the complexity in the data. Yeah, we can talk about that for sure. I mean, right, you're going to be limited by the sample size. So obviously the more data, the better, but it's worth a try. Okay, so we're back on our, we've kind of, hopefully now you get a little of the big picture. And the next step is to actually do some of this stuff. So I have 2 example data sets. We're going to work through each one in the rest of the time we got. The first one is a classification model of dates. So what is the data set? You may have heard of the website Kaggle. That is a site that they do these sort of like predictive modeling competitions. They like put up a data set and say whoever builds the machine learning model that makes the best predictions wins. And they also just have a bunch of free example data sets up there that are like useful for some of these things. So that's where there's a lot of ag examples on there. So that's where I got this data set from. Basically what the data set is they have fruits from date palms that are in 7 different varieties, 7 different genotypes. And somebody took a photograph of about 900 of them across all the varieties. And then they took each of those pictures and used an image analysis software to take different measurements of the fruit, like how the length, the width, you know, the circumference, how long and narrow it is, and that kind of thing. So we have about 900 rows and 34 columns of data. So one row is one picture of a fruit, and so there's 34 variables that they measured on the picture, and then one other column called class, which indicates which variety of date it is. That's what this data set consists of. What are we going to do with this data set? We're going to do basically almost exactly what we just went over in the abstract. We're actually going to do it on a real data set. Import it into R, make plots of it, clean up the data by getting rid of wrong data points and variables that are too highly correlated and won't help us predict. We're going to scale the variables. Then we're going to do a training and testing split, do cross-validation on a random forest model, which is used for classification, and optimize the tuning parameter. Then once we figure out what the best tuning parameter is on cross-validation, we'll see how well it does, how accurately it predicts the varieties on the testing set. So we're going to go into R now and go into Posit Cloud and load the packages that we're going to need for today and import the data. So I'll just mention before we do that, we're going to use tidyverse for data manipulation. Random forest is the name of the package that fits the random forest machine learning model. Caret is the package that will set up our cross-validation and help us do it. And then the other packages are plotting to help us plot the data. And we read the data in from the CSV. Again, it's on It's on a website if you aren't on the Posit Cloud server. And then we're going to go ahead and mutate to turn that class variable into a factor variable. Because again, factor is a data type where it can only have one of several pre-specified values. And so we want the different, the 7 different varieties are the pre-specified values of that factor, the levels. So let's go into our Posit Cloud, and you can open up the same project from yesterday. And we'll go ahead and we want to start with a clean session. So I'm going to go ahead and delete all the variables from yesterday in the workspace and restart R just to make sure we're starting from a clean slate. It's a good practice. It probably won't make a difference, but it's just a good practice. Also, the memory on this demo server is limited, so it's a good idea to you can see it sort of tells you how much memory is being used, which is a lot compared to what is, because this is not like we only have a small amount of RAM on this demo server, so especially good to just get rid of. We'll use the broom to clean up these old objects, delete them all. You can close the worksheet from yesterday. We'll clear the console and we'll restart R as well. And then I'm going to open up today's worksheet, the machine learning worksheet, which is in the worksheets folder. Again, if you're using your own R on your local machine, you would have to download that worksheet. Okay, so see. Let's go ahead and load the packages. So I'll highlight all that and hit Control Enter to run it. And then I left you some blanks here. So we'll read underscore CSV to read it in. And then we'll turn class into a factor variable. So class equals factor of class, turning it into a factor variable. Hit Control Enter to run that. Oops. Sorry, I can't get this little sharing banner to go away. It's blocking me from going there. Here we go. All right, and first thing we want to do is take a look at the data and see what it looks like. So we're going to use dim, that means dimensions. That's going to tell us how many rows and columns are in it. And we're going to use table, the table function on this class variable. If you have a factor variable, the table function will give you a count of how many rows belong to each group. We're going to see if the data is well balanced. And so we'll do that on the worksheet here. First, we're going to use the dim function, dimensions. See how many rows and columns are in the data. Control Enter. Yeah, so we have, like I told you, about 900 data points, and there's 35 columns. One for the class. The rest are variables we're going to use to predict the class. And we're going to use table to take a look at how many of each class are there. Here are the names of the cultivars or the whatever they are, and how many of each. It's good if it's reasonably well balanced. That means you want to have in your training and test set to have a reasonable number of every variety in your training and test set. Because if we split it up, so if there was only like a few then we couldn't get enough information in our training set of those to predict new ones. So we want to have the training and test set be well balanced and have some of everything. So I mean, this is an example data set, so we have some of all. But like if you had only 1 or 2 data points from a variety, you may as well just remove that from your data set and not even try to predict it, because you're not going to have enough information to predict it. But this one has some of everything, which is good. So before we do any modeling, as I said, it's good to look at the data. So I have this code here will plot all the response variables, the box plot to show the distribution of each variable within each class. And let's take a look at that and see what we're gonna do is get a vector of predictor variables. That's all the names of the columns, everything except class. And then we're going to pivot the data set, which helps with the plotting, and then we're going to plot each one. So let's do that and take a look. So they're called predictor variables. Control Enter. You can see it's got 34 names in it, which are the column names of the numeric variables in the data set. Next, we're going to pivot longer, which will turn it just for plotting. We're going to do a long data set. And the columns we're going to pivot is the predictor variables. So we'll fill in all of predictor variables here. This is just for plotting purposes. So now we have a really long, skinny data set with 30,000 rows and 3 columns for plotting. Then this next ggplot command is going to plot them. So let's make the plots, and then we'll comment on what we see in it. We'll have to zoom it in to be able to see it. So what stands out when we're looking at this? These are all 34 variables. So we can see, okay, some of these variables vary more between the varieties than others. Those variables carry more information. Like I don't really even know what some of these are, but like, well, area, the area of the fruit in the image, you can see that there's a good amount of variation in between the varieties. Some date varieties have are large and some are small. So we can say, well, you know, if we have a big date, it could belong to one of these two. That's going to be a decent one to explain some of the variation. Some not so much, like extent. All of them are very similar, so that if we know the extent, we don't have a lot of information about what variety we're dealing with, but some we do. And another thing, okay, here's a weird outlier on this one too. Aspect ratio, the ratio of length to width of the fruit is 500 and something for one of them. That seems wrong, right? A date is like pretty squarish. You couldn't have one that's 500 times longer than it is wide. So that's probably a mistake in the data, I would say. That's not an outlier that's a real data point. That's clearly wrong. So we could get rid of that one without having to worry about it's going to harm our predictive performance. That's clearly a bad data point, I would say. So good thing we plotted the data and saw that. Otherwise, we would have it in there and it might throw off our predictions. And we will just say, instead of trying to like guess what the aspect ratio might be, since it's only one data point, I think the best thing to do is just delete that entire row from the data. That's probably just the easiest thing, because it's only one. If there was more, we could think a little harder about it, but it's only one. So let's just use filter to just nuke that row. And we're going to filter and say aspect ratio less than 500. That means we're going to keep all rows where aspect ratio is less than 500. And then we can use the nrow command to look at how many rows are left after we did that. So we'll say, and again, it's for some reason in this data set, it's all capitalized. So we have to write that just like the capitalization is in the data set, aspect ratio less than 500. Run that. And you can see here we got rid of one row, but just another way to see that would be to use the n row function to take a look. So yeah, we're down to, we were at 898, now we're at 897. So we got rid of the one row that was wrong. Is everyone good in terms of everyone was able to load the data, and has anyone had a problem with that? Sorry, I should have checked on that earlier. Cool. If you do need help, just let me know. Now, the other thing I mentioned we should do is look at the correlation between our different predictor variables. If some of them are almost perfectly correlated, if we know one, we know the other, that's not carrying any new information, so we might as well delete it from our before we, or not use it to fit the model, because it's just all it can do is slow down the computation without giving us any new information. So if two variables have a correlation that's close to +1 or close to -1, we can get rid of one of the two. So this command creates a correlation matrix between all the pairs of predictor variables in our data set. And then this GG core plot is a function from a plotting package that will create a heat map of those correlations. So we'll do that. We'll use the core makes correlation matrix. You can see it's a 34 by 34 matrix, all pairs of correlations between the 34 numerical variables in our data set. And then we'll use GG core plot, CORR plot, and type equals lower means it's just going to plot the lower half of the matrix, the lower triangular, because the correlation matrix is symmetrical. So we only need to see half of it. And let's zoom in. Yeah, so you can see if it's a solid red, they're perfectly positively correlated. If it's solid blue, they're perfectly negatively correlated. We have quite a few pairs that are close to +1 or -1 in the data. Like area and perimeter are almost perfectly correlated. If it's bigger, it's going to have higher area and higher perimeter. So they're just both saying how big is it. Probably one or the other of those would be enough in our model. We don't need both, for example. So this is just a way to show that. So what do we do to figure out which ones to delete? There's a nice function in the caret package, which has a lot of helper functions for machine learning, called find correlation. And we can pick a threshold absolute value of correlation, and it'll identify any variables that are correlated with at least one other variable in the data set at 0.95 or higher. And we can use this find correlation function. Cutoff equals 0.95. Names equals true means it will return the names of the correlated variables. And then we'll use the select function on date fruit, which means select is a function from the tidyverse that will delete columns from the data set. Select negative all of correlated variables means it will delete all columns with names that are found in this vector called correlated variables. So we're going to do that. You could try other thresholds. I think 0.95 is pretty good. So we use the find correlation function. Again, if we start typing it, it'll pop up. We can hit tab to complete. And cutoff 0.95. Control enter. So you can see it is 16 elements long. So it found 16 variables that we can get rid of without losing very much information. And we've called that correlated variables. So now let's select and get rid of correlated _ variables. hit Control Enter. So yeah, now our date fruit data set has the same number of rows, but less columns. We got rid of the correlated variables for the purposes of fitting our model. So far, so good. Next step, we're going to split the data up into training and testing. As we talked about, we're going to take 10% of the data and just hide it, keep it away from the model fitting so that we're never going to use those data when we build our model. We're just going to save that to evaluate and see how good is our model. And again, there is a function in the caret package that helps us with that. Create data partition, which will, like I said, you want to make sure that the training set has a good representation of all the classes, the varieties, and the test set also has a good representation. So create data partition will automatically do the stratified random sampling to balance the varieties in the training set and the test set. And we say P equals 0.9. We're going to have 90% of the data to build the model and keep 10% to test the model. And then the next two lines of code will split up data. Train index will say which rows are supposed to go in the training set. And so then we'll keep those rows for the training set, and then we'll say get rid of those rows, and that'll be the test set. So train index, and we'll keep only those rows, and minus train index will get rid of those rows. So we'll have a training set and a test set, and added up, we're splitting the data in two. Oh, and set seed, by the way, is because create data partition randomly splits the data set. And when you do any randomization, you can set the random number generator seed in R so that this will ensure that when I run this on my machine and when you run it on yours, we're going to get the same randomization will be used. If you change the random seed, it would split it differently. You could put any, this one is just, you could put any number in. I just put one, but you could put any number in, and that'll just make sure that you and I will get the same result, so you can make sure you're doing it right. Yes, Jenna. Okay. Are you doing this on your own?
Yeah.
And did you install it?
Yeah.
I might have forgotten to, did I forget to put it in the list of packages you need to install? I might have. Let me help you.
Yeah.
Okay, yeah, so maybe there's like a package that is dependency, so you'll have to install that one as well. I didn't realize that. So if there's, you can install recipes as well then. Okay. Oh, there's an error, there's no package called lava. Well, I guess I can install lava too. So you're just like, yes, and then you just keep working the package. Try to install lava too, yeah. Okay. Okay. It didn't do it. Yeah. Why don't you restart R and then try to install go ahead and restart R, because sometimes the package is already loaded and won't update. And then yes, then try to install here it all dependencies. So if you do so I ran that one. Did you
Sometimes I think it's the that function might be in another package as well. You have other packages loaded. Did you start on a, did you start the whole session from yesterday? Yeah. Yeah, why don't we decide that we go to the session, we start our side running. Here, try to say, try to say, where install package, hear it, and then the dependency. I'm gonna that will help you. Yeah, because it's not, and then put comma, dependencies. Can be set there, dependencies. All yeah, see, so that document is wrong. Yes, that's right. Why, well, let's see if that works. Can you do that? Yeah. So the select function is also found in a specific column package that we had in the end of the day, so maybe you could go over it. Yeah. Okay, I'll come back to you in a second. Yes. Yeah. So after yes. Okay. I'll be yes, go ahead and, yeah, highlight everything you want. If you restart, the packages will not be loaded. Yeah. And what are you all, keeping up with? Okay. Yes, same. Okay, yep. You didn't restart R before you, so go to session and restart R because some packages that are loaded from yesterday are conflicting with the ones from today. I don't think, well, maybe you did. Well, yeah, now try to run everything up to that line and see if it works. Yeah, you'll have to just highlight everything, yep, and give it a try. Yeah, you can just highlight everything up to the line that you need. Yeah, just go all the way up to 51. Yeah, there we go. Now see if that works. Yep, okay, good. And, did you get Word one? Back. Okay. Well, I'll keep going and we'll check again in a minute. Okay, thank you for your patience, people on Teams especially. We are going to, yeah, so let me see where we need to create this data partition to split the data 90% and 10%, use 90 to build the model, and the other 10% we'll save. So then we'll create one using those rows that we randomly decided to use, the 90%, and then the test set will not have those rows. So we'll do that, the initial training and testing split. So we want to use the create data partition. Again, I can start typing it and then hit tab to complete. The column that we want to make sure is balanced is the class column with a capital C. We want the proportion of training data to be 90%, 0.9. So we'll run those two, train index. You can see there's 811 numbers, which are the rows that we're going to keep in the training set out of the 900. It's about 90%. And
Then we'll say date underscore train. We'll keep those rows, train index. And date underscore test. We'll say minus train index. We'll hit Control Enter on that. So date train has 811 rows. That's 90% of the data. Date test has 86 rows. That's the other 10% of the data. And they're if you want, you can look at the table. I didn't put this in the code, but this will show you table of. You can see that in the training data set, we have as equal as possible proportions of all the cultivars. And oh yeah, if you hit the up arrow in the console, it'll take you to the last line you typed. So then I can just change train to test. And you can see in the testing set, the proportions are the same as they are in the whole data set. So we've split it 90-10. Now, I'm going to take a step back and do a little bit more explaining of what we're about to do, because what we're going to do is fit a random forest model to classify these the dates into varieties based on their measurements. What is random forest? Basically, it's a machine learning model, and the algorithm it uses is it's going to sample the data with replacement many times and fit a decision tree to each random sample. But what is a decision tree? A decision tree is kind of like a way to split up data with a series of rules that ultimately tell you what class or value the data has. So like, let's say you have some animals. Let's say you have an animal and you want to know what kind of animal it is. Well, you can say first, like, well, does it have more than 4 legs? If it does, we say, well, does it have more than 6 legs? If yes, you've got a spider. If no, you have an ant. You know, this will obviously fail if you have an insect that's not an ant, but this is a simplified model. If it doesn't have more than 4 legs, first you say, well, does it have feathers? No, then what you're holding is a mouse. If it does have feathers, is it red? No, then you've got a sparrow, otherwise you've got a cardinal. So that decision tree will correctly classify an animal as long as it's either a mouse, sparrow, cardinal, ant, or spider. Otherwise, it's not going to do a great job. But that's a decision tree. That's all it is. It's pretty simple concept, right? Well, random forest is a tree-based model. Ultimately, it's going to classify those different dates based on a decision tree, but a single decision tree may overfit the data. So what random forest does is it's called random forest because it has a lot of decision trees. It's got a forest of them, and it kind of randomly samples the data a bunch of times and makes a decision tree on each one, and then averages up the decisions made by the tree to make a final decision of how to classify the data. And there's the algorithm kind of sort of does its own training testing within that algorithm to see how well it already is doing regularization in a way by splitting within that algorithm into training and testing. But we're going to like double up and do even better regularization by also doing cross-validation on that. So like inside the random forest algorithm, there's like a training testing split, and then we're going to do cross-validation again. So we're like really doubling up and making sure that this isn't going to overfit the data. Again, that is a very like superficial description of what random forest is doing. You don't really have to understand exactly what it's doing, as long as you understand that it's doing a decision tree and it's like doing some random sampling to make sure it doesn't overfit the data. That's basically what it's going to do. So we're going to actually fit a model now. All we did so far was like get things set up. Now we're going to actually fit the machine learning model. Before, is anybody still behind and hasn't got the code up to this point? I'm happy to help. Yes, are you still not able to load the package? Yeah, that one might take a long time to debug, so I'm not sure. We'll have a break in a few minutes again, and maybe we can try to fix it in the break. So the function that's used to train models in the caret package is called train. It's sort of the main function, and it can train many different kinds of machine learning model. We're going to specify random forest when we do. But the first thing we're going to do is say what method are we going to use to train the model. We're going to use cross-validation to train the model. We're going to use 5-fold cross-validation. So this train control sets what specifications are going to be used to train the model. Method equals, in quotes, CV. That means we're going to use cross-validation. Number equals 5 means we're going to split 1/5 of the data off 5 times to use it to train the model. That's what this line is doing. And then we're going to save that into CV spec, which means the specifications of our cross-validation. So train control with a capital C. Again, you can start typing it and hit tab. CV means cross-validation. 5 means we're going to use 5 folds. 5 is kind of a sweet spot in terms of if you use too many, if the computation is slow. If you use too few, then you have, less than 80% of the data is being used to train, which is not that much. So 5 is kind of 5 to 10 is like a sweet spot for cross-validation. Okay, now we have this super, super long function call with many, many arguments in it, which is like, this here is the training of the machine learning model. So let's go through the arguments of it so you can understand what it's going to do, because this is it basically. Like, this is most of what where the rubber meets the road in terms of actually training the machine learning model. Let's see. Yeah, so the first argument there is form. That's the model formula. Class tilde dot. So that means in our data set we have one column called class. The other columns are all the numerical measurements. And this is like shortcut. This dot means use all the other columns in the data set to predict the class. We're going to, again, well, it's not 34 anymore because we got rid of some correlated variables, but it's any other column in the data set is used in the model. The data argument is the name of the data frame with the data in it. We're going to use the training data. And method equals RF is random forest. And if you click on this link here, it will tell you all the different models that you could specify in that method argument. I'll just see. We'll go to that just so you can get an idea. Oh, whoops, that didn't work. Oh, I see. It's because I didn't put in the URL correctly. Well, anyway, you can use a lot of different. I won't mess with it now, but you can train a lot of different kind of models. And pre-process equals C center comma scale. That means we're going to standardize the variables. We're going to center them, which means subtract the mean, and scale, divide by the standard deviation. So they're all going to be in Z transformed in standardized units with a mean of 0 and a standard deviation of 1. That's going to make sure the model is not going to overly use ones with high numerical values to predict. They're all going to be in the same units. And okay, so the next, there's a bunch more arguments. The next one is tune grid. That means we have to tell it what tuning parameters to try to use cross-validation to optimize. And there's one called mtry. That's the only tuning parameter we're going to use. What mtry is, when a random forest is building the decision tree, it's making a bunch of little splits. Every time it makes a split, it selects variables randomly to use for that split. The more it selects, the more possibility of overfitting the closer it can fit the data because it's using more information, but the more possibility of overfitting. If we do it too few, it'll underfit the data. If we do it too many, it'll overfit the data. We want to figure out where the ideal one is. That's what we're going to use. And what is our loss function? What are we trying to predict? We say metric equals accuracy. That means basically what proportion of varieties are classified correctly. We're going to say the best model is the most accurate that predicts the most varieties correctly, or the most individual dates it predicts those varieties correctly. And then we use TR control to tell it that we're going to do the 5-fold cross-validation. And there's also an additional argument called ntree, which we could use defaults here, but I just wanted to specify this so you can see what it's doing. This is basically how many trees are being generated in each random forest. I said 500. Basically, the higher the better, but the more you put, the longer it will take to run. And so you can kind of just make it as high as you can, and still it runs pretty quickly. So or without making too long to run. So I just put 500. You could make it higher if you wanted to. It might make the model better. So it just like make it as high as you can. Yes. Yes. No, I don't think so, because as I said, the more the better. It will not, it's not going to make overfitting more of a problem. It's just better to use more trees. The more trees, the better. There's no reason to use too few. The only reason to not make it, you just make it as high as you can within what your machine can do. You don't need to worry about optimizing it with cross-validation. You could, but it's not going to make any difference. So I just set one number for that. And then I put importance equals true because I wanted to show later which variables are most important for the classification. And so it will do some computation to calculate the importance values to look at later. Yes, so let's fill in some of those arguments before we go ahead and say what it's actually going to do. So yes, classification, class by all, using date train, use random forest. We're going to scale the data. We're going to try every M try between 1 through 10. We're going to say which one has the most accuracy. We're going to do 5-fold cross-validation. We're going to do 500 trees, and we're going to calculate the variable importance. All that, and it'll just, that's where the magic happens, basically. This is going to fit our model for us. So I've left a lot of blanks in here because I think it's important for you to understand exactly what we're doing as well as possible. So the model formula is class tilde dot, which means use all the other variables to predict class. The data is the training data, date underscore train. RF is random forest. That's our method. We're going to center and scale the variables so they're all in the same units. We're going to say M try equals 1:10. That means we're going to try out every value of M try between 1 and 10. Accuracy with a capital A is the metric. We're going to find the most accurate. We're going to use this CV underscore spec that we made a minute ago to tell it to do 5-fold cross-validation. And we're going to do 500 trees. You could, if you want, put a higher number there to play with it. I mean, that's why you have this code environment. You don't have to do what I do. You can change things up. You could go M try even higher if you wanted. You could put N tree. You could put the N tree in the tune grid as well, but we're not going to do that here right now, but you could play with it. So yeah, that's well, here I'll start it running. I don't think it takes too long to run. Oh, CV spec not found. I didn't run that line of code, so I'll run that. And then we'll run it date train RF. So yeah, what this is doing is it's going to do the 5-fold cross-validation 10 times. First with M try equals 1, then with M try equals 2. Basically fitting the random forest model 50 times, 5 times 10. And each of those 50 is going to grow 500 trees. So it's doing quite a bit of computation. It takes a minute or two to run. So while it's going, I'll say yes. So then it's going to tell us what is the best value of M try that maximizes the prediction accuracy on those 20% of data that we held out on each of the folds. And then it goes back, after it finds that optimal value, it fits the model to the full training set, to the full 90% of the data that it can see. Yeah, so it already ran, so it doesn't take super long with this. It's not a huge data set, so it didn't take too long to run. So let's take a look. We can plot. If we call plot on this, it will tell you the prediction accuracy for each different value of M try that it tried out. We'll do that. We'll plot date underscore RF underscore train. Okay, so here's the prediction accuracy. So what do you think about this plot? Anyone have a comment? What is the M try that is best? 2, right? So we have the highest accuracy. Well, what else can you say about this? What are the numbers on the y-axis? The lowest here is 88.5% accuracy. The highest is 90%. So it's like, well, that's only 1% difference between the worst and best. So we can also say that it didn't really matter too much on our prediction accuracy. So all that cross-validation kind of just told us that it doesn't matter a whole lot. But if we had to pick one, we should go with 2 because it is a little bit better. Okay, yeah, so if you
I think sort of
interesting. Okay, yeah. I wonder if, and are you using the server one or your own? That's interesting. It could be yeah, it could be, and you set the random seed on this as 1 as well? Yes, that's interesting. I wonder if there's also a random seed that's set in here that that might cause a difference. I'm not sure. I'll look into it in a minute. I'm not sure exactly why, but see, that is a good example of why people repeat the entire cross-validation process many times, because a different split of the train and test can give you slightly different results. But again, right, like that kind of emphasizes there's not that much difference in these accuracies. It's like 90 to 89%. So a tiny difference in which data points are used could switch it, because they're not that different to begin with. So because Random Forest is already doing its own regularization internally, our performance of the model is not that sensitive to the tuning parameter that we choose, because slight differences in randomization is enough to swap it around. So it really, the performance is right. 89 to 90 isn't that different. So that's basically the same. So it's just kind of like fluctuating randomly. I'll try to figure out why it's different though. And if you just type date RF train into the console and hit enter, it will give you summary information on the model. It'll say, okay, well, here's the pre-processing, the cross-validation. So right, every time it was using, since we had 800 rows and we're taking 80%, it's doing like 650 each time. And then it's telling us the accuracy each time. So again, they are very close. It didn't make that much difference. One is a little bit worse, but the rest are right around 0.9. I would say it doesn't matter too much which you pick. Another thing we might want to look at is what's called the confusion matrix. That's a matrix that for a classification model tells us for each data point whether we were right or wrong in predicting. So it has, the rows are the predictions the model made of what variety. The columns are the true ones in our training set. So if the prediction and the reality is the same, you're going to have a 1 in the, you'll add 1 to that cell. If you got it wrong, it's going to be, so a perfect confusion matrix would have all the data right on the diagonal and zeros everywhere else, because everything on the diagonal is predicted and true is the same. We got it right. Everything else we got it wrong. So that might not make sense. Let me show you what does it look like by running confusion matrix. Okay, the percent of times that, like this the percent of times of the whole data set where the prediction was Berhe and the truth was Berhe. So that's that happened 5.7% of the time. But a small percent of the time, the prediction was Berhe, but it actually was Iraqi. So like these are where we got it right on the diagonal. They're the same, yeah, and everything else we got it wrong. So a perfect model would have 0 in all of these areas except the diagonal. You can see that it did a pretty good job because we got 90% accuracy. So only, only 0.1% of the time it was wrong this way. For example, some you got a little more, like 1.4% of the time it predicted Iraqi, but it was actually Berhe, for example. So those are like ones you would make a note of that are like commonly wrong. But it never, if the truth was Safavi, it never predicted Berhe. We got 0 there, so that's good. We want to have these ones as low as possible and the ones on the diagonal as high as possible to show accuracy. Make sense? So now, okay, here's the moment of truth. That all was internal within the cross-validation, but we still kept that 10% of the data aside to test the model parameters on and see how well it does on a data set it's never seen before. So we're going to take our 10% of the data set that we split off to begin with and use the predict function to make predictions of those varieties based on the measurements for those dates. And we have to specify what is the model we're going to use to make the predictions. That's the RF train, which was the object from Caret that we use to train the model, or that contains the model. And new data is the test data. So we're going to use the model we trained and predict the test ones. And then we can make a confusion matrix for the test data and see how accurately it predicted the data, the varieties for the ones that it never saw before. This is like as best we can do to see if it's a good model or not. So we'll predict using the model we just trained, and we'll predict on the test data. Control Enter. So now it made a prediction. It's a factor. So these are the model's predictions. Let's compare them to the truth by using a confusion matrix. So we'll use the predictions we just made, and then the class column from the test data, see how well they match up. So yeah, it gives you a lot of other statistics, but here's the so this time it gave us them as integers. So you can see it got 88% right. So we have, there was 4 Berhes in the test set, and all 4 of them were correctly predicted. There was 9 Deglets in the test set. 7 of them it got it right. 2 of them it got wrong. I'm sorry. Oh, there were 6 Berhes. It got 4 right and 2 wrong. Yeah, this is the reference means the truth. So it got but it didn't get too many wrong. Most of them, the ones on the diagonal, are the ones that got right. So it got about 88%. And you can even see these extra statistics of like how well it did on each of the classes as well, but we won't get into that too much. How many false positives and false negatives it had, basically. Yes, come on. Right. Yes, I'm not sure exactly how it calculates that. I would have to look into that. I haven't. I'm not sure, but yes, it's giving us some sort of test statistic to get a confidence interval on that 88% accuracy and a p-value. Let me look into that and figure out how it got. I don't know the method of computation it used to get that, but it's basically saying, well, the p-value is the no information rate is 0.23, right? If it guessed completely randomly, right, with no information, if you just guessed out of these 7 varieties and just guess randomly, it says you would get it right 23% of the time. So is 88% significantly greater than 23%? Yes, by a lot. Clearly, you were doing a lot better than random guessing. That's what I don't know how they calculated it, but it's showing that we did better than random guessing. It probably uses like a multinomial distribution to get that, I would say. But that's basically what it's saying. Another thing I wanted to show you, I mentioned that there are ways to use random forest models to actually look at what variables are most important to make the predictions. And there's a function in Caret called var_imp, variable importance, that can do that for a lot of different types of models. And what it tells you is the mean decrease in accuracy when you remove a variable from the model. So like if length was really important, it would have a high value for mean decrease in accuracy, because if we remove length from the model, does it make the model a lot worse? If we took out a variable and it doesn't change the model performance much, then it's not important, right? And so type equals 1 means we want overall importance, not 1 for each class. And scale equals false gives us the raw importance values. Otherwise, it will scale them as percentages. So let's take a look at what this tells us. We want this var_imp with a capital I on the model. Type equals 1, scale equals false. So here's how much did the prediction accuracy go down by when we removed each variable from the model. So it looks like area, the size of the date, is the most predictive of the variety, because when we fit the model without area, it got 34% worse at predicting. But all of them have at least some, since we got rid of like correlated variables and everything before we did this, all of them are at least doing something. So we, there's no 0 here. It just goes down to 14. So, but area, whatever entropy is very important for determining the variety and that kind of thing. Compactness, roundness. So they're all different shapes and sizes. So that might be interesting to you. I don't know why, if you're interested in predicting date varieties, but that's what you would look at to see what is most important for that. And we'll take a break in just a minute, but the last thing we're going to do with this date example is I wanted to show you that you can use that train function for all different kinds of machine learning models. I just told you that if you're doing prediction, you don't really care what model you're using. You want the one that gives you the best results, because that's where the money is to be made in the date predicting business, is getting the best results. So we can say, well, random forest got 90% accuracy, but that's clearly we could go up to like 99 or whatever. So like, let's try some other models and see if they do better. Now, this time, I'm not going to tell you like what's going on under the hood. I just wanted to show you that you could use this same train function for different type of machine learning models. There's another one you may have heard of called support vector machine, SVM. It's just another classification model. So all we have to change is the method argument to change it to support vector machine, and tune grid, because it has a different regularization parameter. It just so happens, instead of mtry, it's called C. That's the parameter in a support vector machine that determines between overfitting and underfitting. If it's a small number, it is more underfit. If it's a high number, it's more overfit. So we're going to try out different C values. So yeah, you can see that all these arguments are for the most part the same as before. We have the same formula, the same data, the same pre-processing and metric and five-fold cross-validation. Only difference is SVM linear is the specific type of model we're going to train. And this sequence 0.021 by 0.02 means we're going to try out every value of C between 0.02 and 1, 0.02, 0.04, 0.06, all the way up to 1. So you never want to just stick with defaults for this. I had to look in the documentation of the model to look at what a reasonable range of values is. People often assume that whatever defaults are good. That's not necessarily a good assumption. You never know why somebody put default values in. You should always, when it comes to these tuning parameters, always look and see you have to actually read in the documentation what it means and come up with a reasonable range. Otherwise, you're not going to get good results. So yeah, I just called this SVM train. So we're just going to real quick try another one out and see if it does better, just because we can. So here we go. Just because we can. So we'll do that. Train a support vector machine just for grins. So it's called SVM linear. C, capital C, is the name of the tuning parameter. We're still going to use accuracy. And CV underscore spec was the five-fold cross-validation. We're going to run it. Package is needed and is not installed. Well, I will go ahead and install that. You may see that message as well. I didn't configure the demo server correctly, I guess. I'll make a note of that for next time, since it's the first time I did this. So now that it's done the installation, it's running the SVM model, which will take a minute or two. And yeah, once it runs, we'll take a look using the same stuff we did before. We're going to plot to show what tuning parameter was optimal. We're going to predict using this model on the test data, and we're going to make that confusion matrix just like we did for random forest and see if it does much better. So yeah, this one is a little bit more computationally hard, so it's taking a bit longer. So yeah, here's all the code that we're going to run in a second. Still going. Yeah, so it is almost 11:30. That's when I said we would be done, and this is like the last thing we're doing on demo number 1. I have a whole nother one, but we're kind of out of time in terms of the schedule I set. So would anyone be? Yeah, I mean, obviously none of you have to be here, but I can stick around a little bit longer if anyone is interested. After we finish this example, we can take a quick break and do a little bit more, or we can call it a day. Can show of hands, who would like me to go through the rest of this? Or just like right now, I guess. Sorry, what was that?
Hey, this is Carolina. I would like to see the rest of the workshop.
Okay, sure. Well, then we'll just okay. So at least a few people are keen to have more. So we'll after this example, we'll take 5 and then do, hopefully in half an hour, we'll knock out the rest of it, and then like at noon we'll break for lunch, and then we won't break for lunch. It'll be over then. Yeah. So okay, we just finished running the SVM model, and yeah, we're gonna plot, we're gonna predict, and then see how well we did. So let's do that. First, we'll make the plot. Again, maybe somebody will get a different result than me if the random seed was different. Okay, so here's the plot again, right? Here's like, okay, the optimal value of C was around 0.03, but again, we can see that it wasn't too sensitive because even the worst one was 89.5% accurate. The best one is 91.5. So it's like, okay, that's like a little bit better. I mean, maybe that's enough to make a difference between, you know, a loss and a profit or whatever it could be. I don't know. We might as well go with this one because it's a little bit higher than the rest. And we'll do the predictions, run that line of code, and generate the confusion matrix to see how well we did. So again, we got actually just by chance, we did even better on the test set than the training set. We got 93% accuracy. So the random forest model got 90%. The support vector machine was a little tiny bit better with 93%. Again, well, the confidence interval on that accuracy is between 85 and 97. So that might not really be that different. But it's like, well, the two models were comparable in how well they did, but maybe this one did a little bit better. So because we can use whatever one we want to, because all we care about is accuracy, we can say, well, let's just go with that one, you know? It's all about what results you get. So yeah, that's does anyone have okay, so we're going to finish up here with the last little bit of content. We don't have as much left since we've kind of done everything very methodically. We're going to kind of gloss over some of the steps for this last example, but I just want to give you one more example. Since I told you at the beginning, we did that machine learning can do classification. If you have a categorical variable that you're trying to predict, it can also do regression if you're trying to predict some continuous variable. Like if you're want to know yield, obviously that's a continuous variable that we might want to predict. So we're going to do that for some sugarcane yield data. And right, if you're in the sugar biz, where the money's at is tons of sugar per hectare. That's what you want to maximize. And it's a continuous variable, so we're going to do a regression to see how we can predict it. Now, this is some real ARS data that I got from a scientist, but I kind of like added random noise to it just to anonymize the data a bit. But it's real data. And the data, it could be real, it could be not. I don't really know for sure, but this one I know is real. And what they did was they took a hyperspectral camera that collects different wavelengths of light when it takes a picture. And they took a picture of a bunch of plots of sugarcane from a drone that was flying over there. And it took a picture of all the plots and recorded basically the reflectance, how much of each different wavelength of light is coming off of that sugarcane. And then they use those. They're sort of like, if any of y'all are doing this stuff, they have things called vegetation index, which is like a variable you calculate by summing up and multiplying the wavelengths in different ways, can give you different index of how healthy the foliage of the sugarcane is. Some people think that that is related to how much yield you'll get of sugar later on. So this came from some kind of randomized complete block study where they had different varieties and different treatments. I just excluded that information from this demo. We're just going to pretend we don't know any of that stuff, and we're just trying to predict just off of basically the color of the leaves. Can we predict how much sugar is in there? Because that would be neat, because especially with sugarcane, it's a perennial crop that grows for multiple years. So if you could get an advanced prediction, it would save you a lot of time later on in breeding trials. What are we going to do? We're not going to use random forest this time. We're going to use lasso regression, which is a special kind of linear regression. Right, linear regression meaning we're using a bunch of predictor variables estimating a bunch of slopes to predict a response. But the difference of between a regular linear regression and a lasso regression is just one thing. The lasso regression has an extra parameter, lambda. It's a regularization parameter, just like the other tuning parameters we already talked about. Lasso regression has a tuning parameter as well, lambda. And what lambda does is, again, just like all the other tuning parameters, strike a balance between overfitting and underfitting. If lambda is high, it causes some of the regression slopes to shrink towards zero or even go to zero and drop out entirely. The larger lambda is, the more that happens. So the more, if you have a very high lambda and more coefficients go to zero, will that make more overfitting or more underfitting? Anyone want to guess? If more of the slopes are zero, will it fit the data closer and be overfit or less close and be underfit? Underfit, yes, that's right. You had a 50-50 shot, that one. So the yes, the more of the slopes are zero, the less the data is being used to predict. So it's going to be more likely to be underfit. If lambda is small, it doesn't restrict the overfitting as much. So you want somewhere in between. If you, right, the high lambda gives you a simpler model, which doesn't fit the training data quite as closely as it would as a standard linear regression would, but it's less overfit. It will make better predictions on the new data. You want to get it in between somewhere and make the best predictions on the new data. So before we actually do the machine learning model, let's do what we do as usual, which is read the data in and make a plot of the of all the variables. First, we're going to import the data. Then, so the columns are a bunch of predictor variables, and our Y, the one we want to predict is TSH, tons of sugar per hectare. And because it comes from a block design experiment, we also have a column for the rep. So we're going to figure out what predictor variables we're going to use by saying we're going to take all the columns except for our prediction outcome and rep. And then I have some code to make scatter plots of all of them with a little trying to show if they're related to TSH. And I've added a smoothing line on there just to help you visualize. So let's do that. I didn't give you any blanks there. So you can go ahead and, well, first we'll run this. You can see it has 144 rows and 20 columns. So it's got rep, the Y variable, and then all these different wavelength and vegetation index data that they got off of the drone pictures. There's 18 columns of that. The sugarcane predictor variables has 18 names of columns. Now we're going to plot them. This code just makes a big matrix of plots. It added a smoothing spline onto each plot just to help you visualize. So yeah, this is the relationship between all these wavelengths that was taken off the drone picture and sugar yield. So it's like, well, okay, like maybe if you squint, some of them are like a little bit going up, those lines, like some of these variables, maybe as you know, this variable gets higher, sugarcane yield goes up, you know, ish. Some are not, like this one is clearly not predictive whatsoever of sugarcane yield. It's completely flat. But some, it's like, okay, like maybe there's something here, like maybe we have something to go off of, I would say. Next thing we do is, as we did before, some of these variables might be correlated with each other. If we know one, we know the other. Having multiple correlated variables in the model is not going to help us. It's just going to add noise to the model without helping the prediction. But I just wanted to, I'm not going to actually remove them ahead of time this time because we know that the lasso regression can actually get rid of those uninformative variables. So I wanted to you how it can help do that without removing the correlated variables first. If you wanted to, you could later play with it and see what happens if you try different ones. But I did want to just show the correlation plot just so you can take a look at that. So we'll look at that. We want to use the core function to make a correlation matrix of the sugarcane predictor variables. So if you start typing that, you can see you can go and hit tab and it'll finish typing that for you. We'll make the correlation matrix and plot it. So I'll just highlight that and run the code. And let's take a look. So yes, some of them are very highly correlated, right? Like, because these wavelengths are sort of overlapping a bit. So like many of them are very highly positively correlated. Like this, this vegetation index is, all the vegetation index are calculated from different functions of the wavelength data. So some of them are very similar to each other. It's kind of like how green are the leaves. So like they're all different ways of measuring how green are the leaves. They're not that, they're very highly correlated. And but we're just going to leave them all in and see how the model does dealing with that correlation itself. Any questions so far? Cool. So we'll keep forging on, and I decided to not bother with the training and testing initial split this time, and just do cross validation. So we're just gonna kind of see how we do and not worry about the final evaluation just for this example. It would be nice to do that in practice, but in the interest of time, we're just gonna do just do cross validation. But remember that I told you we can't just do it randomly, decide which folds are, because we have a randomized complete block design. We don't want to. We have 6 reps in our in this study, and we don't want to split up the reps in between our cross validation folds. We want to fit a model to 5 of the 6 reps and use it to predict the one we held out. And we're gonna do 6-fold cross validation, and this code here. So instead of splitting up the data randomly for each fold, this actually will manually define the folds based on the reps. So we basically create a list for each of the 6 folds of which rows in the data go with that block, and then send that to our train control function to tell it we're going to do 6-fold cross validation with a predefined split that we came up with based off of what block each data point goes in. So yeah, we're going to fit this model 6 times. First, we're going to fit it like on 1 through 5 and predict 6. Then we're going to fit it on 1, 2, 3, 4, 6 and predict 5. We're going to repeat that until all have been predicted. If that makes sense. Hopefully it does. So we want to map means we are going to repeat this function 6 times, 1 for each fold. And we want to say which sugarcane $rep, that means which row in the sugarcane data in the rep column is equal to that number. Then we're going to send that to method CV number equals 6 and use those folds we just defined. We'll do that real quick. So sugarcane $rep with a capital R, and then that's gonna be our cross validation rule that we're gonna send to that train control function. We're gonna do 6 folds, and the rows in each fold is gonna be index out is which rows will be used as the prediction. The test set each time, CV_folds that we just created. Control Enter to run that block. Now we're going to use cross-validation, we're going to use that train function again like we did last time. So you remember how it has the model formula. But this time we're gonna give it the X and the Y. X is going to be the matrix of all the predictor variables, all those wavelengths, and Y is going to be the tons of sugar per hectare. And the function, the package that is used to where the function for lasso regression is called glmnet. We're going to specify that as the method. We're going to scale all the variables just like we did before. And our tuning grid is going to be our lambda tuning parameter. We're going to vary it by factors of 10. Again, I had to look on the documentation to see what is appropriate. And there's another parameter alpha in there. We're just going to set that to 1. I won't go into exactly what that's doing. Now, since we don't have a classification accuracy we can use anymore, what we're going to use is our root mean squared error. So we want the model that minimizes the error in yield. Whichever tuning parameter gives us the best predictions of yield, the closest, minimize the error, that's what we want. Our MSE is root mean squared error. That's what we want to minimize. And then we pass our cross-validation folds to the train control to tell it we're going to do 6-fold cross-validation. So yes, maybe the reason last time, I think you have to set another random seed before. Hopefully now we will get the same results. I think if you set a random seed right before you do this, it should give the same results. If it doesn't, I'm not sure why, so we'll have to figure that out. But yeah, basically we're gonna say these are the predictor variables are gonna be used as our X, tons of sugar per hectare is Y, glmnet is the function we're going to use to fit the model. And here are all our tuning parameters. We're going to minimize our MSE and use this cross-validation rule that we just created. So let's do that. And that'll train the lasso regression. So the Y, let's see, I put a different seed in this script, 923. Well, hopefully that will work and give the same result. So sugarcane, $TSH is our prediction outcome. glmnet is the name of the package that's going to have the lasso regression in it. Expand.grid creates a grid of parameters. And the name of it is lambda, is the tuning parameter we're going to optimize. And the metric is RMSE that we're going to minimize that. And that CV underscore spec underscore sugarcane is the one that we're going to, the cross-validation that we decided we were going to do. So we'll run all that. I'll just leave that for a second so people can see what I typed in, and then we'll run it. Oh, another packet. Okay, yeah. So this is another thing. Again, I haven't taught this before, so there may be some technical kinks in there. I have to make a couple notes here. Okay, I think it already did the lasso. It only took a second. It's not. It's already done running. So. Okay, so we'll take a look at how did we do. We'll plot the object to see what value of lambda gave us the lowest error. So remember last time we were trying to maximize accuracy, so we want to see where that line was highest. Now we're trying to minimize error, so we want to see which one has the lowest error. So let's do that by plotting it. So we'll plot it. So you can see that basically the error gets worse and worse the higher that lambda is getting. The best one is that lowest number. I don't know, did you all get the same looking line or different? It got different, yeah. So we'll have to look into why exactly that is. But another point to look at is that these, it ranges from 5.7 up to 6. That's like how much the yield prediction was off by every time. And the yield, the sugar yield. So basically, none of these models is really that good because the best we could do is predict the yield within 6 tons of sugar per hectare. That seems like for 5.7 was the best we could do. That's like a pretty big error. So even, our best possible model that we can make off this data is not very good. That's kind of why I use this example data set, is to show you that these things are not magic. And if there's not information in the data that can predict, we're not going to be able to just magically like get a good answer, because there's just a lot of maybe there's just not a lot. Those drone images just don't do a good job of predicting the yield. There's other random variation going on that's predicting. So we only, even though some of these values are better than others, the best we can do is not very good. So that's kind of the lesson here, I think. And you can look at this best tune will tell us the optimal value of the lambda parameter was this small value. So it actually did better with a low amount of regularization. It didn't, we're trying not to penalize for overfitting very much. And where were we? So, and if you just type the name of the model into the console and hit enter, it will tell you the prediction, RMSE, how much error was for every lambda that we tested. We'll try that. Yeah, you can see all the different lambda values. Here are the RMSE, and it also gives you an R squared. So like you could also have said we're trying to maximize R squared. The best one we got was 0.27 about, which isn't very much percent variation explained. And you can see that like it does get worse as we down to 0.18, but the best we could do is 0.27. So maybe that's good enough for what you want to do, but probably I would say that's unlikely to be good enough to actually something that you could use in practice. You wouldn't want to fly a drone on some new sugarcane and take pictures and say we know something about the yield using this model, because you're going to get it pretty wrong. You're not going to do a great job predicting. So yeah, again, sometimes the answer is we don't know, and this model isn't good enough to use. This is just kind of a proof of concept to show that the lasso gives you a slightly different result as a traditional linear regression. And what this does is basically pulls out the best lambda and gives you the coefficients, the slopes from the lasso model, and compares it to a linear regression model where we didn't do any regularization. So let's try that. And this is just sort of a proof of concept. So let's see, I've given a few blanks here. So this one, we want to say in the final model, we want to find the lambda value that is closest as possible to the optimal one we decided to use, and then get the coefficients corresponding to that value of lambda and plot it or make a table of it next to the ones from a traditional linear model and see how different they are. So we'll want to find the lambda from the final model, but also lambda here that is closest to the optimal. And then get the coefficients from that model. And then we're going to put the coefficients from the lasso model next to the ones from the linear regression model. And we'll run that whole thing. We get an error. Oh, whoops! I left some dotted line in there. Well, I should have put lambda there as well. So we'll go over and put lambda there too. Hopefully that works. Yes, so here we go. So that this is on the left-hand side are the slopes from the lasso model. On the right-hand side are the slopes you would get if you just fit a linear regression to the data. You can see that none of them are quite zero, but some of them on the traditional linear regression are very large. And it looks like we did the lasso shrinks coefficients closer to zero. So it's the traditional linear regression is overfitting to the data a lot more so than the lasso regression. So even though we decided this model wasn't very good and wouldn't be good enough to use in real life, you can see that it's doing something to help balance between overfitting and underfitting that a traditional linear regression is not doing. Like this slope is minus 107 here versus minus 6 on lasso. So that's just to demonstrate what it's doing. It's making them closer to zero. Right, like it's instead of 201 here, it's 8. It pulled it closer to zero to make it a more general model that does better on new data. Even though it doesn't fit the original data as closely, it does better on new data. But still not very good in an absolute sense. Yeah, so again, we could try other types of regression model. You don't have to use lasso, but if there's just no signal, if there's no information in the data, your best model in the world of the most sophisticated model is not going to save you. There's just no information there to go off of. So that was kind of why I use this example. Yeah, that was all in terms of the demo. Or before I wrap up, does anyone have any questions on that? Yeah, so I just wanted to recommend, if you're interested in learning more about the basics of machine learning in R, the one book that I would use that's like by far the best is called Introduction to Statistical Learning. That's the one I first read when I was first trying to get into this stuff. And it explains all these machine learning models very well and in a way that anybody I think can understand. And the people that wrote it like invented lasso regression and other machine learning techniques. So they really know what they're talking about and are very good at explaining it. There's two versions, like there's Introduction to Statistical Learning and there's Introduction to Statistical Learning in R, which has specifically R examples. So I would get that one that would be the one I would recommend. There's also, so all these, I have links to all this. If you go to the slide, you can click on these to get to the website for all this stuff. Applied Predictive Modeling was written by the person who wrote the Carrot package. And then I mentioned tidy models at the beginning. They do have a bunch of tutorials as well you might want to look at. But yeah, I think this is all. You can get a free version of the book as a PDF for all these things. They're available online. But I mean, it's nice to have a paper book too, but you can get it for free online. Yeah, that was my last slide. So thanks a bunch for sticking around to the bitter end. And I apologize for some of the technical issues with this last lesson, but now that I've done it one time, I will be able to like go back and figure out why there was some discrepancies in the output for people. And next time I do this, I'll have that figured out, I promise.